Good morning to everybody. We are passing on to the third part of unit and measurement. This is nothing but errors in measurement. In physics, we are really dealing with properties of matter. While interested in measuring the properties of matter, we need a scale. In order to construct a scale, we need a unit. By means of properly calibrating the scale, which is internationally accepted, we can measure a quantity. While measuring a quantity, we are going to commit some errors. How to rectify the errors? What are all the types of errors? How physics can aim at absolute measurement? That is a topic that we are really interested. Now let us get into the topic. So dear friends, we are really interested in learning about error and error analysis. Here, there are so many terms that are really very, very important. Let us go one by one. Now, error in measurement is the topic. Generally, what is called error? Error is nothing but the difference between the measured value of the quantity to its true value. For example, an object is having a length of 5 centimeter, let us suppose. 5 centimeter is the true value. By using a scale, I can able to measure the value as 5.2 centimeter. 5.2 is the measured value. What is the error? 5.2 centimeter is the measured value. 5 centimeter is the true value. The error is 0.2 centimeter. Error in the measurement is not a mistake. It tells how accurate the instrument is. The more accurate, less error. Inaccurate, uncertainty, variation, deviations are the other name given to the error. Now, here in this particular chapter, we want to classify the errors. We want the method to reduce the error. Our ultimate aim is by physics, by actual measurement, we want to measure the true value closely. So, now let us go to the things. Measurement is the foundation of all experimental science and technology. Physics' absolute aim is going for measurement. The results of every measurement by any measuring instrument contain some uncertainty. The uncertainty is called error. Every calculated quantity which is based on the measured values also has an error. We shall distinguish between two terms, accuracy and precision. So clearly we say measured value, true value, the difference is called error. Error can be reduced by means of taking a high resolution instrument. By means of high resolution, what we really mean, we can make the instrument to measure accurately close to the real value. So we want to learn about the difference between accuracy and precision. These two terms are really very, very important. We need to understand the things. Accuracy of a measurement is a measurement of how close the measured value is to the true value of the quantity. Whenever we make a measurement, we are supposed to be accurate when the measured value reaches the true value. Precision tells us to what resolution or the limit the quantity is measured. For example, measured value has got high resolution, then it may ensure us that we are really going very close to the true value. But accuracy and precision are entirely different. Accuracy says how close to the true value. Precision says how under what resolution we are really making the particular measurement. The accuracy of the measurement really depends upon so many factors. For example, a true value of the length is 3.678. We are using vernier calipers to measure and the value is 3.5 centimeter, let's suppose. Let us use screw gauge of resolution 0.01 centimeter to measure, but the measured value is 3.38. By screw gauge, the value is 3.38. By vernier calipers, the value is 3.5. Which is accurate? 3.678 is absolute. 3.5 is one measured value. 3.38 is another measured value. Though the resolution of 3.5 centimeter is 0.1, but it is really close to the true value, so it is found to be correct. So, whatever may be the resolution, how close to the true value defines the measurement correct or wrong. So we know accuracy means very close to the true value. Precision means resolution. How good the resolution is, how accurate the measurement is. When both of the things are close together, then the measurement is considered to be very, very close. For example, let us consider the hit target, the bullseye. Red is really making the bullseye. Complete red targets the target the bullseye. The blue dot is really concentrating on a particular point. The blue dot is precise, but it is not accurate. The red dot is precise, but also accurate. So let us know the things. Accurate means close to the true value. Precise means how close the value is. So close, accurate is a very, very important term in measurement. So precision is the degree of closeness of the measurement with each other. Precision means whenever we make the measurement, how close the measurement is really decides the precision. Precision often referred as repeatability or reproducibility. Precision is getting consistent results of the repeated experiment. Whenever we do the experiment, whenever we measure, the instrument is said to be precise when the readings are very close to each other. But accuracy is the degree of closeness of the measurement to the target reference value. Accuracy often referred to the Bayes error. Accuracy is measuring near to the target of the true value. See the graph. The green line really represents the reference value. The average measured value, true value, difference says about the accuracy level. But the spread really says about the precision level. Measured value spread really speaks about the precision. The difference between the average value and the target value really says the accuracy. Here, three cases. First cases, all the hits are on the target, very close to each other. So it is said to be no error, high accurate, highly precise. Here, all the shots are very close to the target, very close to the target. So highly accurate, but it is spread, so it is low precise. Here, all the hit is very, very close, but it is away from the target. So very close, high precision. Away from the target, low accuracy. So we are getting so many things now. Accuracy, precision, true value, error. So accuracy is the closeness with the true value. Measurement can be accurate, but not necessarily precise. Single measurement defines the accuracy. Accuracy may be affected by systematic error. Accurate value had to be precise in most cases. Accuracy defines the degree of conformity to the true value. Measured value close to the true value defines the accuracy, defines the degree of conformity. Precision is the measure of reproducibility of the measurement. Measurement can be precise, but not necessarily accurate. It needs several measurements to be determined. Precisions may be affected with random error. Precise value or may not be accurate. Precise defines the reproducibility degree. accuracy degrees the conformity. Accuracy close to the true. Precise closeness to the measured value. So, we have already seen the difference between the measured value and the true value gives the error. How close to the true value gives the accurate value. How close are the measured values gives the precise. So, there are two types of error generally we mark. One is called systematic error. Another one is called random error. The systematic error are those errors that tend to be in one direction, either positive or negative. Random errors are those errors which occurs irregularly and hence they are considered to be random, but the sign may be both the sides. These can arise due to random and unpredictable fluctuation in experimental conditions. While measuring the resistance, if temperature varies, resistance varies. Voltage supply varies, resistance varies. Mechanical vibration, experimental setups, so many things can cause the random errors. Personal and observational persons error can also cause the random errors. So, systematic errors are the error caused only because of the instrument. Random errors are caused by so many conditions. Now, errors can be generally be classified as systematic errors, random error, gross error. Random error. Suppose we are taking the measurement for a ring, the mass of a ring in 3 times, 15.46, 15.42, 15.44. The values are slightly different, but when we take the average, we can able to arrive near to the absolute true value. Systematic error. Suppose the cloth tape is used to measure the length of an object. Due to the year long, the cloth tape may be stretched and it may not be at the true exact form. The error caused by the deformation in the measuring tape is considered to be a systematic error. The error in the instrument causes a systematic error that may be either positive or may be negative. Random error may be due to the observer. The average of the measurement can able to give the nearest value to the true. Here, systematic error. There is an error in the measuring tab. So all the measured values are very close to each other, precise to each other, but there is an error. Random error. The error may be due to experimental conditions, environment, personal bias, so that the error may be different in different directions. Random error may be positive, may be negative to the true value, green line, to the true value, green line. But systematic error, because of the instrument, either it may be positive or it may be negative, but it is only in one direction. So, errors can be generally be classified as random error, systematic error, gross error. Systematic errors are the errors because of the instrument. It may be because of the observational, because of the environmental, because of the instrument. Systematic error is the error to the true value, either in one direction. It may be caused due to instrumental error, environmental error, observational error. So, systematic error causes instrument, environment, personnel. So, by means of having a zero error in the instrument, we are really measuring the measurement. The measurement is having the error because of the zero error. By means of improving the structure of apparatus, by means of giving the zero error correction, systematic error can be reduced. Second thing, random error, parallax error, incorrectly using the apparatus, or inappropriate usage, experimental setup error, parallax error can cause the random error. By means of repeating the experiment and taking the average can reduce the random error. So, systematic error can be classified into three types: instrumental, environmental, observational error. For example, while measuring the mass of a jar, initially there is an error of 2 milligram, means automatically in every reading the error is added. So this type of error is called instrumental error. This can be reduced by means of doing the zero adjustment. In the Geiger-Müller counter, while measuring the radiation, if we keep our cell phone error, the radiation will also be counted and added to it. This is called the environmental error. The third error is while taking the measurement, if the observer makes a parallax error, there is an error in the measurement. That error is called observational error. Instrumental error, environmental error, observational error. These three are causing the systematical error. So, the first bullseye really say all the targets, all the hits are on the target, all the hits are very close to the true value and very close to the real value. So, the first bullseye target is accurate, precise. Second one is all the hits are on the central circle, but it is spread somewhere. So though there is accuracy, precision is not there. The third one, precision is exactly there, but it is not nearest to the true value. So the last one is called systematical error. Spread in the true value gives the random error. No spread, accurate is considered to be no error. So, instrumental error that arises from the error due to the imperfect design or calibration of the measuring instrument. Zero error in the instrument. For example, while doing the temperature graduation, if the thermometer is already having 4 degrees, if we measure the boiling point of a water in the STP, we are going to get 104 degrees. That 4 degrees is the instrumental error. In vernier calipers, vernier 0 should coincide with the main scale 0. If there is no coincidence available, there may be an error that is called zero error in the vernier calipers. This type of error is called instrumental error. Likewise in screw gauge also. To determine the temperature of the human body, rather than using the thermometer in the mouth, when the doctor uses the thermometer in the armpit, actually the temperature is considered to be, the measured temperature is considered to be less than the actual value. The external condition or the technique used can able to cause an error. This is called experimental technique or procedural error. Personal error that arise due to the individual bias, proper setting of the apparatus, individual carelessness in taking the observation will cause this type of error. Parallax error is a one type of error. So, personal error, instrumental error, experimental setup errors can cause the systematic error that can be minimized by improving the experimental techniques, selecting the better instrument, and removing the personal bias. We can reduce the systematical error. Generally speaking, measurement should be accurate. Measurement should be precise. Precision of the instrument really says the precision of a measurement depends upon the least count of the measuring instrument, resolution of the measuring instrument. Vernier caliper resolution is 0.1 centimeter. Screw gauge resolution is 0.01 centimeter. So, according to the length measurement, screw gauge is considered to be doing the precise measurement. The smaller the least count, more precise is the measurement. What is called accuracy in measurement? The accuracy in measurement depends upon the number of significant figures in it. Larger the number of significant figures, higher the accuracy. If there is no error in the instrument, then that measurement is most accurate. Least count 0.1 centimeter, the instrument gives 5.6 centimeter. Least count 0.01 centimeter, the instrument gives 5.45 centimeter, but the true value is 5.764. Whatever may be the resolution, identify the measured value. One is 5.6, another is 5.45. What is the true value? 5.76. Which is nearer to it? 5.6 is nearer to it. Though the resolution is 0.1, the value is nearer to the true value, so the first instrument measurement is accurate. So first measurement is more accurate but less precision. Second instrument is less accurate but more precise. We should know the differences between accuracy and precision. How consistent a series values are close to each other defines the precision. If you have several measurements, if all those similar measurements are close to each other, then the measurement is subject to be precise. For example, John measures the amount of tea in his mug by 4 readings: 100 ml, 101 ml, 102 ml, 101 ml. Actual measurement is 120. The measurement is 100, 101, 102, 101. But here, all the measurements are around 100. So the measurement is precise, but the actual is 120. It is far away. Though the measurement is precise, but it is not considered to be accurate. Now, let us see an accurate measurement. Ram measures the amount of tea in his mug 3 times: 119 ml, 116 ml, 115 ml. The actual amount of tea in the mug is 120 ml. 119, 1 ml away. 116, 4 ml away. 115, 5 ml away. 115 is least accurate. 119 is the most accurate. So, how close to the real value says about the accuracy. Now, let us know the differences much more better. For example, the volume of the liquid is 20 ml. Now there is a set of reading: 20 ml, 19.3 ml, 18.8, 18.6. Out of the 4 readings, 20 ml is the reading, so the accuracy is really good. But the readings are not so close, so precision is very poor. Second one, 16 ml, 16.1 ml, 16 ml, 16.2 ml. All the readings are encircling around 16, so the readings are precise but not accurate, far away from 20 ml. Third one, 20.1, 20 ml, 20.2, 20.1. All the readings are close to 20, so it is precise. All the readings are close to the true value 20, so accurate. Accuracy is also good, precision is also good. Last one, 18.6, 17.8, 15.6, 16.2. The readings are well spread over, so precision is less. The readings are far away from the real value, so accuracy is also poor. So close to each other means precise. Close to the target value means accurate. So here in the first case, the target is hit, but the readings are widespread, so precision is poor, accuracy is good. Here, the targets are close to each other, so precision is good, accuracy is poor. Fourth one, all the hits are widespread, so accuracy is also poor, precision is also poor. Last case, readings are close, hits are very close, hits are on the target, so accuracy is also good, precision is also. So, whenever we are doing the measurement, measured value, true value, difference says about the accuracy. How closeness of the measured value says about the preciseness of the measurement. Measuring process is essentially a process of comparison. In spite of our best effort, the measured value of the quantity is always somewhat different from the actual value or the true value. The difference in the true value to the measured value of a quantity is called error in measurement. The errors can be classified into 4 types: absolute error, mean absolute error, relative error, percentage of error. Now, what is meant by absolute error? It is the magnitude of the difference. Note the point. It is the magnitude of the difference between the true value and the measured value. Difference actually in positive sign alone. It is the magnitude, not with sign. It is the magnitude of the difference between the true value and the measured value. Okay. Next, mean absolute error. It is the arithmetic mean of the magnitude of the absolute error in all the measurement of the quantity. We are taking 10 measurements. We are taking the average of the 10 measurements. Rather than taking the average, it is the arithmetic means of the magnitude of the absolute error. Out of the 10 measurements, we know the true value. The difference between the true value and the measured value is going to give the absolute error for each measurement. All the 10 measurements, we calculate the error, absolute error, and calculate the mean absolute error by means of doing the average. Next, relative error. It is defined as the ratio between mean absolute error to the mean value. Absolute error is nothing but the difference between the true value and the measured value. The mean of the readings is going to give one value. The differences between the ratio of mean absolute error to the mean value of the quantity is known as relative error. Percentage of error when the relative or the fractional error is expressed in percentage. When the relative or the fractional error is expressed in percentage, we call it as a percentage of error. Let's see the example. Generally, a quantity's value can be represented as x plus or minus delta x. The length 7.58 centimeter plus or minus 0.05 centimeter really says 7.8 centimeters is the measured value, 0.05 centimeter is the error in the instrument. Error can be classified as absolute error, relative error, percentage of error. All the three says about the uncertainty in the measurement. Absolute error is the amount of error in the measurement. Absolute error delta x is modulus of measured value minus actual value. So 0.05 centimeter in the above reading is the absolute error. Absolute error is always positive. For example, absolute value of volume is 20 ml. Measured value is 20.1. The error is 0.1 ml. It is always considered to be positive. Relative error. Relative error is nothing but it is the ratio of absolute error to the actual value. Absolute error to the actual value. Delta x by x is going to give the relative error. Delta x by x is going to give the relative error. 0.05 is the absolute error. 7.8 is the measured value. 0.05 by divided by 7.8 is going to give the relative error. Percentage error is nothing but multiplying the relative error by 100, it is going to give percentage of error. Absolute error by actual error into 100 is going to give the percentage of error. 20.1 is the reading. 0.1 is the absolute error. 0.1 divided by 20.1 into 100 is going to give the percentage of error. So, propagation of error while doing two measurements, A and B. For example, I want to measure the circumference of a rectangle or a square or something else. So I am going to measure the length and I am going to measure the breadth. While measuring the length, I am going to commit some error. While measuring the breadth, I am going to commit some errors. What will be the error while calculating the circumference? For example, x is equal to a plus b, let me suppose. Delta A is the absolute in the measurement of A. Delta B is the absolute in the error in the measurement of B. Delta X is the absolute error in the measurement of A plus B. That is nothing but X. So delta X, percentage of error in the value of X is nothing but delta A plus delta B plus or minus is called error in the X. Percentage of error means delta A plus delta B divided by A plus B into 100. Likewise, if X is equal to A minus B, the absolute error in X measurement is delta A plus delta B. Percentage of error, delta A plus delta B by A plus A minus B into 100. A minus B into both the things for addition and subtraction. Delta A plus delta B, addition means A plus B, subtraction means A minus B into 100 is going to give the thing. Sum A plus B. Difference also A plus B. Difference also A plus B. Delta A plus delta B. When X is equal to A cross B, delta E is the absolute error in the measurement of A. Delta B is the absolute error in the measurement of B. Delta X is the absolute error in the calculation of X. Delta X by X, fractional error is equal to delta A by A plus delta B by B, that is the fractional error in X. Percentage of error means percentage of error in value of A, percentage of error in value of B. Likewise, when we are dividing the quantity X is equal to A by B, delta A absolute error, delta B absolute error in B, delta X is the absolute error in calculation of X, delta X by X fractional error is equal to delta A by A plus delta B by B, that is nothing but fractional error value of A plus fractional error value of B. Next, actually we are really interested in seeing about the order of magnitude. In scientific notations, the numbers are expressed in the powers of 10, decimal powers. M into 10 power x is the general representation when n is a number lying between 1 to 10 and x is an integer. Order of magnitude of quantity is the power of 10. X, the order of magnitude of a quantity is the power of 10 required to represent the quantity. For determining these powers, the value of the quantity to be rounded off. While rounding off, we ignore the last digit, which is less than 5. If the last digit is 5 or more than 5, the preceding digit is increased by 1. Speed of light, 3 into 10 power 8. 3 less than 5, so we leave it. 10 power 8 is the order of magnitude. Mass of electron, 9.1 into 10 power minus 31. 9 is greater than 5. So 10 power 1 into 10 power minus 31, 10 power minus 30 kg. That is order of magnitude. Scientific notation is the way that is used to handle very large numbers and very small numbers. Given the number 56303030. Now we are having 3, 6, 9 zeros succeeding 56 number. Now we can have 5.6 into 10 power 10, where 10 power 10 is the exponent form. 5.6 is the digit form. Likewise, we can able to say, convert any number into scientific notation. 4.82 into 10 power 5. See, given number, we got a point. After the point, we are moving towards the left, shifted to the left. 1, 2, 3, 4, 5. Now we get 4.82. 4.82 into 10 power 5. Next one, moving to the left, we have to go to the 8 digit to reach 4.67. 4.67 into 10 power 8 is nothing but the scientific notation. Last one, 1.0 into 10 power 6. If decimal is shifted to left, then the exponent is always positive. If decimal is shifted to left, the exponent will be always positive. If it is turned to right, then it is always negative. We are given so many examples for shifting it to right. Here it is known as scientific notation. Next, we are passing on to another very, very important property called the digit, called significant digits. Significant figures, the digit which are correct or accurate on the level of their measurement resolution. For example, 6.3 is the actual measurement, but the reading is between 6.3 to 6.4. We are making it 6.35. We can write the significant digits up to the least count. The resolution is 0.1 centimeter, and the other digits after the resolution is considered to be insignificant. So in the measured value 6.35, 6.3 is the accurate value. 0.05 is not accurate because it is above the least count. So we are now going on to the significant figures. All leading zeros are not significant. Point number 1. All non-zero numbers are significant. All non-zero numbers are significant. All leading zeros are not significant. All non-zero numbers are significant. All zero between the non-zero numbers are significant. All trailing zeros after the decimal are significant. See in the below figure, 0.000, 0.000, 700623, 0.400. In this particular number, leading zero are not significant. Zero between the non-zero numbers are significant. All trailing zero after the decimal are significant. We noted the significant figures here. 2000 trailing zero. So 2 is only the significant number. So significant is only 1. 2.00 trailing zero. Actually, leading zeros are not significant. All trailing zero after decimal are significant. 2.000 is significant to 4 value. In the scientific notation, only digital term is considered to be significant. 6.07 into 10 power 4, where 6.07 is significant, 3 digits significant. Likewise, 1000, actually significant digit is 1. 1000.0 got 5 significant digits. 0.350 has got 3 significant digits. 560, 2 significant digits. So we must apply the rules and we can able to do the particular things called significant figures. So rounding off, basic rules, actually, if the next digit is 4 or less, 1, 2, 3, 4, leave the previous digit as it is. If the next digit is 4 or less, 1, 2, 3, 4, leave the previous digit. If the next digit is 5 or more, 5, 6, 7, 8, 9, increase the previous digit by 1. So 7, 5, 3, 4, 9, 6, round up to 4 digits. 7, 5, 3, 4. For example, the next digit is 9, more than 5. So we add 7, 5, 3, 5, 0, 0. Round to 3, 7, 5, 3. The next digit is 4, less than 5. So leave it 7, 5, 3, 0, 0. So 2 digit, 1 digit, we already done. So rounding off is another very, very important rule. So non-zero numbers are always significant. In between zero are always significant. Leading zeros are never significant. Trailing zeros are somewhat significant. So these are all the rules we are going to apply for significant digits, rounding off, and we have also seen scientific notations, how to add, how to subtract the significant figures also we can see. In the next class, we can see how this error concept can be applied to the problems in physics. Thank you.